My name is Seth Roseworm. I'm a senior structural engineer and a software developer here at ENERCALC. And our presenter for monthly ENERCALC office hours is Mac Calterhoni. Mac is a senior structural engineer here at ENERCALC, and he kind of splits his time between providing technical training for ENERCALC customers and working with the ENERCALC engineering team on specifications and behavior of our software, as well as helping maintain a presence for ENERCALC at national and regional events. Mac is also the founder and managing principal of Elta Design Group, which is a specialty engineering firm specializing in cold form framing design. He's been an ENERCALC user for about a decade, so he has a lot of insight about the needs of our customers. He's worked in everything from engineer of record work to specialty engineering to um, many other types of structure design. So, for anybody who's new here this month, Office Hours program provides direct communication between us and our customers. There's several different things we do every single month. We mainly showcase new features and updates from ENERCALC. We also show optimized design workflows. We answer prepared questions that users have sent to us ahead of time. We also do live Q&A every single month with our audience, with our customers who attend. And if there's ever a question that's too involved or requires deeper digging and research, then that's a better fit for discussing with our support team. But as always, we definitely encourage you to reach out with any questions you have. As a minor point of order, you will notice that everybody's microphones are muted just to make sure we don't get any echo or feedback. We do have open Q&A in every session, and so to submit a question, just go to the Q&A dialog in the lower dashboard of your Zoom window. If you experience audio problems at any time during the session today, you can always either refresh your browser or jump out and rejoin the session, as well as using the default Zoom audio controls in your interface. If you ever want to rewatch today's program or share that with someone on your team who wasn't able to attend, we always have those recordings posted to the Office Hours playlist on ENERCALC's YouTube channel, which you can also access via our website from the Office Hours page on enercalc.com. We do have a special event happening today during our Office Hours session in honor of Pi Day 3.14 at the end of this week. Today, we're holding a special giveaway during our Office Hours session. So we're going to be drawing an attendee from today's Office Hours at random to receive one of our limited edition ENERCALC Lego retaining wall bookend sculptures. Mac is going to announce the winner at the end of the webinar. The drawing will happen sometime during the session for someone who is present during the webinar. And then at the end of the session, if you're still present, then you'll be announced as the winner. So you must be present both at the time of drawing in the center of the session and at the end when the winner is announced. And we'll reach out via email to get your Lego sculpture prize mailed out to you. With that, I will go ahead and hand it over to Mac to get going on our program for today.
Hello, everyone. Thank you, Seth, for the great introduction and the housekeeping, taking care of that. And welcome to another session of our monthly installment of the Office Hours program. And as Seth said, I am Mac Calterhoni, and I am excited to be presenting to you today the 2D frame module from ENERCALC's library of diverse and extensive modules. So without further ado, I'd like to start our session with a brief overview of the overall agenda. Today, we will be covering ENERCALC latest build. We will be covering Pi Day giveaway, which is a structural engineering themed Lego. And we'll be talking about the Steel Conference and giveaway. And then we're going to talk about what's new in ENERCALC. We're going to dive into the meat of the 2D frame design. We'll register for Office Hours to get notified, and then we'll do the winner announcement and live Q&A at the end of the session. First, as always, I'd like to encourage you all to check your software to make sure that you are on the latest build of ENERCALC. And if you could all take a minute, just open your software, take a look at the top, and you'll be able to see your current build that you're on. We do release monthly updates, and we want to make sure that you and all of our users are taking advantage of the newest features and program capabilities. Every now and then, commonly, we receive actually support questions from our users where they might have a problem or an issue, and typically that issue has been addressed in a recent update. So it will save you a lot of time if you're always on the latest and greatest to make sure that you are taking advantage of all the fixes and bug updates that we take care of. So to do this is very simple. You go to the top right corner where you'll find the update button. If you just click on that, that will take you to this window where you can check for updates and launch the for our user, this button right here, for our users page. Once you go there, you will be able to download the latest and greatest updater file. And once you install it, you'll have the latest and greatest build of ENERCALC. If you would like the program to automatically check for these updates at program startup, you can make sure that this is checked. This option right here is checked, so it always lets you know if there is something new. A quick note here for the users who are within these builds, so from 2023 830 to 2024 228. If your software is stuck or if ENERCALC is stuck at any of these different builds between within this range, then the function to actually let you know of the new updates, the function that automatically notifies you of new updates, doesn't function properly. And for you to be able to fix that, you'll have to do actually a one manual update, just like how I showed you, where you click on the update button and you click then on the for our users page and do that a little bit manually on your own. But it's a one-time thing. The current build that we have as of today is 2025 0226, which is the February 2026 edition. So with that being said, let's move on here to the next slide, and that's if you prefer to be notified about office hours via email. You can just scan this QR code, or you can fill in your information right here, and you will be and you'll receive notifications via email about the latest updates. Moving on to the Pi Day giveaway. That's the fun stuff. Just quickly to celebrate Pi Day, we want to make sure that the ENERCALC team decided to give you guys a custom Lego to a one winner that will be picked during the session. And of course, the one item that's important is that you'd have to be present to win, so don't miss out. And this is what it looks like, just to get you guys excited a little bit. It's a fully functional bookend, and this is a real photo of Seth's steel manuals and codes right here. So it's very functional. It works, and it has a perforated pipe right here, just in case you really care about the details of your Lego bookend. Moving on. So ENERCALC is excited to be an exhibitor at the 2025 AISC Steel Conference coming up in April in Kentucky. We have a large 20-foot booth, and our booth number is 582. If you plan on attending the conference, make sure to stop by our booth because visitors will be entered to win a composite steel beam Lego structure. You can see it right here. It's definitely, there's a lot of good work that took place there and to build this. So props to Seth. We will ship it to you, so don't worry about stuffing it in your bag if you win. And we are, of course, conveniently located right in front of the lunch station. So if you are planning on attending, please stop by and say hi to our team. All right, so now if you have not been using the latest build, or you haven't had time to poke around in ENERCALC for a while, or anytime recently, we want to highlight a few of our new features and functions. And also we have a brand new feature that was just released last month. So would like to let you know about that as well, so you can take advantage of it. So the feature that we've had now for a few months that's significant is the ability to decouple the IBC and the ASCE editions. Some jurisdictions started mixing and matching these the design standards. So for example, a jurisdiction might has the IBC 2015 as their code that we have to follow, which is, referencing the ASCE 710. However, they want to use a different ASCE version. So they want to do IBC 2015 with maybe ASCE 716 or 722. So previously, the codes were all, or the design standards were all lumped up together based on the IBC that references them. So if you're in IBC 2015, then you're using the the ACI, for example, 2014, and you're using ASCE 710. But with this new update, now you can mix and match. So you can say, I want IBC 2018 with ASCE 722 to be able to meet, your local jurisdiction's requirements. The second update is the addition of the new ASC 722 modules. I'm sure y'all have noticed that we started with adding 3 new tabs to the calculation menu. And this first tab right here is the seismic loads tab, where we added calculation modules for the seismic base shear, seismic wall anchorage, and seismic demand on non-structural components. The next item here is the next tab is the wind loads tab, and we added a few more modules, which covers the wind load for the envelope procedure based on Chapter 28, directional procedure based on Chapter 27, and we have a wind enclosure calculator. And we are actively working on the component cladding per Chapter 30. It's currently in active development, and whenever it's done, it will be housed under the same wind loads tab right here, in this area. And so yeah, make sure you keep your eye on all the new updates that we release. Next, the last tab we have here is the other loads tab, and currently it houses a live load reduction calculator, and it houses the snow loads that came out about a month and a half or 2 months ago. That's the snow load ASC 722 snow load module. So another exciting update is the native load linking within ENERCALC. So for a few months now, we've had load linking, which load linking gives the user the ability to automatically link reactions from one calculation to another, and the ability to change something in one member and have the effects of that change trickle down to all of the downstream members. So this was one of our most requested feature from our users, and we're excited to say that we support it for steel beams, and it's here, it's ready for you to use. And load linking for other modules is actually an active development. And I've been saying this for the past couple months, and to follow up to follow up on that promise that other modules are indeed in active development, we are super excited to say that ENERCALC native load linking now supports wood beams. This means that you can link reactions between multiple wood beams. Also, this is fully capable of cross-operability with other modules. So that means you can link a reaction from a steel beam to a wood beam, and then you can do it the other way around, where you link a reaction from a wood beam to a steel beam. So as we roll out more support and support for different modules, we're always looking out, and we want to make sure that we allow for cross-linking between these different materials and different modules. So to give you an idea, so if you actually open your any wood beam calculation, so in this example, what I did is that I created wood beam 1 and I created steel beam 1. Those are 2 calculations that are already created. And then I started to create wood beam 2. So once you open a wood beam calculation, you will be able to see this new tab now that says linked loads, similar to what we did in steel. So it'll have the same thing here for wood. And now on the left-hand side, you're able to see steel beam 1 and wood beam 1. And it's the same process. You can click on steel beam, and then you'll see here the 2D sketch updating to show you what you clicked on. So this is the beam that I created, and you can see that we linked this reaction number 1, 0.96 and 0.87, and indeed that's what we have here, the 0.96 and 0.87. In the same calculation, in the same fashion, you can click on the second beam, which is the wood beam, and again, it will show you a 2D sketch of what that beam looks like and what kind of loads are applied on it. And we're grabbing the load from support number 2, and that is the 0.309 and 0.2, and that is shown right here. So again, the engineers at ENERCALC understand that linking reactions from different materials is critical, and it's pretty common. So we want to give our users the ability to mix and match and we're mindful of load linking interoperability as we continue to develop more load linking integrations with our modules. So, of course, the user still has all of the same capabilities in terms of linked load or linked reactions placement. So you can, do the same thing where you can grab whatever load you want and you can put it at a specific location or maybe at mid-span, third points. All of the various options that were available in the steel beam are also available in the wood beam. The standard load linking features are still functional after the wood beam integration or linking load with wood beam integration. So we still have here the calc order, and now it looks into steel beams and wood beams and figure out the exact load path, and it follows that load path properly. So there's going to be no issues with the load path logic, and all the calculations will be performed in the load path order. At the bottom, you can still see the load linking status badges. These apply as well to steel beams and wood beams. So this way you'll know if there's anything that changes, it'll turn from green to yellow or maybe from green to red based on the type of change and the type of the warning status or the type of warning or information that we're trying to convey. And of course, at the very top, you'll still find the Recalculate Linked Loads button, which allows you to bulk recalculate all of your calculations at once to ensure that the most up-to-date reactions are being used and their effects are indeed trickling down to all of the downstream members. So overall, load linking is an even more powerful tool now than it was before with just steel beams. And it allows, of course, our engineers to create well-connected chain of calculations to minimize the risk of transcription errors. And now that we support the wood beams in addition to steel beams, and of course with more to come, the sky's the limit. So if you would like to learn more about load linking, please check out the load linking playlist on our YouTube channel. You can just go to YouTube and then find ENERCALC, click on playlists, and you will find different playlists there. But this one here for load linking will walk you through the process step by step and show you the warnings and gives you a lot of good information. And we do have some other playlists as well. The most recent one we uploaded, I think a couple of weeks ago, that is a full walkthrough of how to use the composite steel beam module and all of the various features, all of the capabilities, and how to get the most out of it. So that's a good playlist to watch if you're using the module for the first time or you want some sort of a refresher. And the last item that we want to highlight before we get into our 2D frame module is our ENERCALC for Revit. ENERCALC for Revit is a Revit plugin that allows you to design structural members fully within Revit without having to export information to another calculation software. It's really a simple point-and-click workflow that allows you to design a member in a fraction of the time that it would take you otherwise. You just click on the member and follow the guided prompts that we have there, and before you know it, you have wrapped up your design and you're done with it. It's really that easy. And the same process, because a lot of people ask this question, and this is not just for framing members, but this is also for foundations. So the same process applies to foundation design. All you have to do, again, is point and click, and a foundation calculation will be generated automatically for you with all of the load takedown from the columns and all the framing members. And so currently EFR supports the design of steel beams, supports the design of composite beams, wood beams, steel columns, foundations, of course, which now you have a full gravity load path, again, with more integrations to come. Once you have the ENERCALC for Revit plugin installed, it will appear inside of your Revit ribbon bar, just like any native Revit option. ENERCALC is an authorized Autodesk developer, so EFR is designed to play nice and interop with Revit. And that, of course, contributes significantly to the dynamic and seamless integration between the two products because they communicate back and forth in real time instead of relying on outdated methods of manually exporting and importing analytical stick models and um, all of the turn of the century type of processes. So moving on, the focus of our session today is the design of 2D frames in ENERCALC. This includes a variety of planar frames such as trusses, single-story or multi-story frames. Many applications, a lot of buildings do not require full 3D design and analysis. And this module, the 2D frame module, is a very useful and powerful tool for all of our ENERCALC users to analyze those, trusses or maybe the one-off or the 2 or 3 moment frames they might have or the knee brace frame they have where they don't really need to model a full building, but they still want some robust analysis and design capabilities, for a lateral system or maybe for a uniquely shaped truss or something of that nature. So here's a quick overview of the capabilities and features of the 2D frame. So it performs analysis and design of steel and wood members. It has a frame wizard that helps you with the initial setup of your frame geometry, frame or truss. You get full control over joints as well as member and fixity conditions. You can apply loads to members as well as joints. Dynamic 2D sketches that respond to the member or joint selected. So if you select a joint, it will actually light up, or if you select a member, it will light up in the model, and that helps creates this dynamic and visual correlation between, of course, what you see and what you're clicking on. Results include the results are extensive. You get a variety of things, but the one that I want to highlight, of course, the one that we always try to get is joint displacement, member forces, and of course, stress checks. Axial shear moment and deflection diagrams for each member, and you get 2D sketches displaying deformed and undeformed structures for visual checks. So we're going to just do a simple example of a moment frame, and we'll kind of work our way through it to give you a good idea of what we're working with. So in today's example, and this is a very common thing that engineers design, especially whether it's a wood building that has a lot of glass and you need to fortify it with some sort of a moment frame, or even a regular steel building. We get these all the time. So we want to design a moment frame that is 15 foot tall and that is 10 feet wide. We're planning on using these sizes, so an 8x8 column and a W14 by 22 beam. The base is pinned, and then the beam to column connections are fixed. So it's a moment frame that's pinned at the bottom here and of course fixed at the top. And we have a lateral point load on the frame of 7 kips. This is ultimate. And we have a gravity load on the frame or on the beam here of 200 PLF. We're trying to make this simple, but you can do a lot more than what we're doing here. But this would be just a simple example that we can dissect a little bit and dive into. So to start a new 2D frame calculation, we follow the same familiar process to start any module. You click on the Add button, and then you click on the Analysis tab, and then finally you jump to the 2D frame. What's unique about this is that once you click on it, ENERCALC will ask you if you want to use the frame wizard, which is this little question right here. If you don't have to use the frame wizard, if you click no, then you'll just have a clean module where you'll have to draw everything from scratch. So you'll have to draw your joints first and do the connecting members and all of that from scratch. However, normally what I would do when I work is that I just click on yes, and I have enough variety here where I can get something to start from and then manipulate it later if I need to. But for most of the stuff that we would need, which is again a single bay or maybe a single bay moment frame, single story or multi-story, so the various things that we typically need are already here in the template. So for us, we're just going to start with a single bay 3-member. That's 1 story and a single bay moment frame. And again, you can pick whatever you want from here. So for us, we'll just pick this and then we click on next. In this window, we set the frame geometry. So we input the horizontal length, which is 10 feet from our example, and we put the frame height, which is 15 feet. Moving on, this is very, very intuitive. We pick the member sizes that we want to use. So you can click, you have here, this is the steel library, and this is the wood library. So for us, we just click on this right here, and that will pull up the AISC section library. We pick the 8x8 by 3/8, and then we do the same thing here where we pick the W14 by 22. If you picked on the wood, then of course you'll get the NDS wood section library, 2x4s and all the various things that you can use. And that's typically something that I would do if I'm working on a truss, but not for typical moment frames that would be steel. So anyways, once you're done with all of this, you click on finish. And the frame wizard will take, I don't know, take 10 seconds, 15 seconds to just auto-generate the frame for you so you can get started. So the layout of this module is slightly different. You can see we have a lot of buttons on the left, on the top here, a lot of taps, more than what we are normally accustomed to in the other modules. So because of the versatility and all of the options that you have, all of the results that you get, we had to jam pack it a little bit with tabs, but it's a very simple process to go through it from left to right. So starting with the general tab, that's the easiest place to start always. So starting with the general tab, you have right here the description. So we'll just put 2D moment frame. And again, I'm saying here that's pinned at the base because that's what we want to do. Next, you get a summary. This is something that I typically look at the very end. And this is a summary about your current frame. It tells you maybe the total number of joints, total number of members, how many loads, joint loads are applied, how many member loads are applied, and all that. So this is more of at the very end. You kind of want to get some overall information about your frame. That would be the place to do it. The user will have the option to pick if they want just analysis and no design checks. So if you're just doing this, maybe you're designing with aluminum or you're designing with cold form steel, you're doing something that is not, hot rolled AISC steel or wood, and you're using just something different, you might want to just use this for analysis capabilities. Then that's all you have to do. You can just click on no checks here. But since this is a steel members and it's design, we will choose the design methodology that works for us. I typically design in ASD, so that's what I will be choosing. However, if you do your designs in LRFD, you can of course do that by clicking on this. Then the users will have the option to pick the global Y sign convention. This right here is critical a little bit for you to understand. So the question is this: do you want the positive Y loads to act in the positive Y direction, aka act upward? The positive Y direction is upward. That's the globally opposite. The positive Y globally is up. Negative Y globally is down. When you want to apply your dead loads, do you want to apply 200 PLF, for example? Do you want that to automatically act downward? Or do you want to say, if I put 200, then I want it up. If I put minus 200, then I want it down. Typically, all of my gravity loads are going to point downward. So I don't want to care. I don't want to really use the global coordinate. I don't want to use the negative Y direction being down and the positive Y being up. I want to reverse it. But this is only for inputting loads. This is not for the overall calculation of the forces. This is still following the right-hand rule. This has nothing to do with that. This is just me saying that I want to use the global positive Y loads to act downward. That's all there is to it. So anyways, I picked this option right here, which is very intuitive. On the right-hand side, we get this sketch stick frame to help us visualize what we modeled so far, which makes sense. That's all we need is just these three stick frames. or these three sticks. So moving on to joints and loads. So under this tab, we have three other subtabs right here. You have joint data, you have joint loads, and joint results. So we start with the joint data. You can see on the left, we have all of the 4 joints and their X and Y locations. And that would be right here, all of your 4 joints, and that's all their locations. You can order these joints however you want. Currently, I have them ordered based on the label. So the joint label is 1, 2, 3, 4. If you click on X or Y or restraint, then they will get reordered, whether it's ascending or descending order, but they will get reordered based on that. So if you want the X, then they do it based on the X. I like to just keep this simple and keep them ordered based on the joint label. That's the easiest way to go about it for me. And of course, right here, at any given moment, you always have the ability to model more stuff. If you want an additional joint, you can model. If you want an additional member, you want. If you want to delete a particular joint, you can. So there is there's that capability as you go through the whole process. So also on the right-hand side, you can see that we have 2 options: joint sketch or full frame sketch. Currently, this is the full frame sketch where I get to see the whole thing. And because I clicked on joint 2, it's highlighted right here. Now, if I click on joint sketch, that would be the next option. This is what it's going to look like. It will just show me that joint by itself, and it will only show the members they're framing into it. And of course, with a label. So member A frames into it, member B frames into it, and it doesn't show me anything else. I like to see the whole thing. And again, it's important to note that in both sketches, the joint that is selected is overly exaggerated to make sure that the user can easily identify that joint. So we click on joint 2. This one is already large, and this one is super large. So that will just that graphical exaggeration is dynamic. So as you click on maybe joint 3, then this one right here will get exaggerated. If you click on joint 4, then it's this one, and so forth. Lastly, this is the fun part of today's session: boundary restraints for joints. So we need to define boundary restraints for joints, and I like to think of these restraints, joint boundary restraints. I like to think of them as an external stability and boundary condition. So for example, this frame does not have any external restraints that hold it in place except for the foundations. Everything else it can move. If it needs to move, it will move. Nothing else is preventing it from doing so. The only part that we have right now that's holding this frame in place is this foundation on the right-hand side and the foundation on the left-hand side. So that will be joint 1 and joint 4. So what I will do, I will pick joint 1 and I will pick joint 4, and I will make them fully restrained. So to dive into this a little bit, if you look right here, you have the X translation. That means movement in the X direction. X direction is left and right. That's just the horizontal movement. So that's, of course, restrained. The Y direction is the up and down, and that's also restrained. The Z rotation, and we recently changed the naming here to say rotation instead of just saying Z, because ENERCALC already knows this is planar analysis. ENERCALC is not confused. It doesn't think about the third axis. It knows that that's not going to be a problem. That is already out of the issue right now, out of the process. So that's not something that we're worried about. This is not meant to represent a third dimension. Instead, this is meant to represent the rotation. This is, if you have moment or if you don't have moment restrained there or not. The reason that we want to restrain the Z rotation, this is rotation that we are restraining in the as a boundary condition. If we don't restrain it there, and then we turn around in the member end fixity and say, oh, the member is also pinned, then this system is no longer stable. So we have to say the foundation is rigid, the foundation is good, the foundation isn't moving anywhere. And then we can figure out what we want to do in terms of having a pin-based or a fixed base. So this restraint is needed in order for the frame to be stable, and it does not mean that the foundation will be taking any moment. Remember, again, for this project or for this frame, we are modeling it as a pin-based frame. So with that being said, I want you to remember this because later on when we see the results, I will show you that the Z rotation or the reaction, the moment reaction at the bottom is zero to fully prove that the base is pinned. So based on this, we fully restrain both of the bases at joint 1 and joint 2. And since 2 and 3 have no external boundary that's holding them in place, nothing from the outside that's holding them in place, hence these two joints are actually unrestrained. So we get here now to applying some joint loads. To apply joint loads, the example requires us to put 7 kips wind load at the top of the frame, acting horizontally. So we select the joint that we want to apply the load to. And as you cycle through the joint, of course, the full frame sketch at the bottom shows you the location of the joint. And indeed, it's this one right here because we clicked on joint 2. This is extremely useful if you have a truss or something that has 20 or 30 or even 40 joints. Then sometimes your labels are not labeled right, or you're trying to make sure that you to do something. This always is critical to click on it and see which joint that lights up to just make sure that you are indeed working with the joint that you want to be working with. So with that, we want to pick joint 2 and add load, and then we have to pick the direction of the load. This is horizontal, so global X, and then we can apply the load that we want under the wind category, which is 7 kips. And again, you can add, copy, delete loads as much, however you want, without any problems. Next step is the members tab. And I want to just go back here. The reason I skipped joint results because we're still not at a point where we're evaluating results. So this is not something for us to worry about just yet. And we can get our results even from a different place. So we'll get back to that joint results if we need to look into deeper information. So moving on, member loads. It's a similar style. We have member data, member loads, and member forces. This is similar to the joint results. This will have the forces that's going into each member. So this would be something for us later to look into if we need to. So starting with member data, you can organize the members, of course, based on how you prefer to organize them. That's why we click on these. We're just going to keep them organized based on the member label. And you can see here that they're named A, B, and C. So the bottom right has a dynamic sketch, a dynamic 2D stick frame type of sketch. And if you click on whatever member you want, it will actually light it up here in orange. So we clicked on member A, then that is member A. So this way, always making this graphical and visual correlation. Each member is labeled with the location of the I and J in this middle one right here. So this sketch shows you where joint 1 is and where joint 2 is. And then the table will tell you member A, the I portion or the I is at joint 1 and the J is at joint 2. So we know that the I is down here and the J is up there. This is very critical because now we're about to determine these end member releases, and we want to make sure that we understand which end is I and which end is J. So now that we understand how to come up with which one is I and which one is J, there are two ways to work this out, to work the releases. Either doing it manually from this table right here, or using the quickset end fixity options that ENERCALC provides, which is very simple to use. Just doing the manual way of going about this. So to do it manually, let's start with the first member A. So we know the first member is a column. We know that it starts at joint 1, which is I, and it ends at joint 2, which is J. So this controls the base of that column, and this controls the top of the column. That makes sense. So the base of the column, we know we want it to be pin. Pin means no movement in the movement in the X or X translation is unreleased. The local Y translation is not released either. So these two are prevented, but then the rotation is released. So this one can rotate freely because it does not transfer any moment. So that is released. That's the bottom. Now, if we want to move on to member J or to member J end, which is the J end, which is the top one here at joint 2 or the top of the column, that one is connected to the beam and this whole area is fixed. It's fixed from the column side, it's fixed to the beam side, it's fixed everywhere. So that will be the X unreleased, the Y unreleased, and the Z rotation or the moment is also unreleased. That's the way to go about it. Then you pick the next member, for example, which is this one right here. We know that this member is fixed on the left, fixed on the right. So it's fixed on the I and fixed on the J. That means it's unreleased, unreleased, unreleased for everything. And then you work your way around. That's one way of going about it. The easy way of going about it is to pick this member. We know the I is at the bottom. We know the J is at the top. We get to tell it what we want it to be. Do we want it to be pin? Do we want it to be fixed pin? The first portion of this is for the I. The second portion of this is for the J. That's why you have fix pin, and then you have the opposite, which is pin fixed, based on where the I is and where the J is. So for a regular column like this, the bottom or I is pin, the J is fixed. Then if you just click on A and then click on this option, it will auto-select the items that you need right here, or the releases that the proper releases to get you where you need to be. This is very easy to build a frame without having to think too much outside of the standard terms of you saying, pin and fixed. And again, you can always add and delete and generate members and do a variety of fun things here. So now that the frame is nicely set up, we figured out how to set the frame up. I want to apply member loads. And in this example, we need to apply dead load of 200 PLF on the beam. So you simply click on the member from the menu on the left side, which is right here. You pick whichever member you want. And if it's a point load, then you apply it in this top table. And if it's a distributed load, you apply it at the second table. So this is a distributed load that we want to do. So the process is to click on the add button right here. So yeah, you click on the add button and then you pick the Y direction or the global direction, which is Y. And the way that we can do this, you can actually determine the start and the end location of the applied load. If you leave it all at 0, then it will be fully distributed. But if you want to say from 0 to 3, then you'll have to put the numbers. Otherwise, it will assume that it's fully distributed. And then again, you can, so this way you can create partially uniform loads if you want. And you look at the same idea right here. You can put your dead load. If you have a trapezoidal or triangular load, then you will put maybe 200 here. And then at the end, maybe it's 400 or something like that. But if it's fully uniform, then the start load and the end load or the end values are all the same. So the cool thing is that every time you pick a member from the top left menu, the sketch below changes. And I'm talking about this sketch. Right now it's for the beam. It shows you a beam. If you clicked on A or C, it would actually show you a column. So you're always having this visual confirmation. And lastly, you can check your member end releases on the sketch. You see that? So we know that this is that's a quick place to review as well. You have the beam member. This says unreleased on all 3 of them. So again, that's a good place for you to do a triple check that you have the right information. So moving on to the next tab, that's just the sections and materials tab. This is the you can control section data, material data by clicking on just the appropriate tab right here. We can start with the section data. Here you can define sections to to be used for your design. So for example, you can, of course, add and delete sections. Currently, we have the HSS 8x8 for columns and W14 for beams. And if you click on the group name, which is columns, for example, if you click on the group name, this actually shows, this table right here gets populated with all of the members that belong to this size and to that group. So that's really handy, again, just to see that everything is done right. For you. And if you click on this HSS or on the W14, that will open up the AISC library to allow you to change members if you need to change the size. And of course, you can do this with Wood as well with the NDS library. So the same idea here applies at the material data tab. There's steel, there's wood materials already defined, and you can also add your own general material or delete a material as you please. And since wood has different species, you can actually click on this button and this will take you to the NDS library of materials. So you can, choose whatever, and species, of course, to choose whatever you want to use. And additionally, if you click on a particular material, you can see the sections that are associated with it. So if I click on steel, it automatically tells me, hey, you have these two steel sections. And we can create different steel materials because this one has an FY of 50. Well, if I have an angle or maybe an HSS even, maybe 40, if I want a yield strength of 46 or 42 or a pipe or maybe 36. So I have the ability to use whatever, I can create whatever material I want here and use that based on the member section that I'm using and the true FY value of that material. So once you do all of this, you can jump to the load combinations tab. I will not dive deep into this one since it's a very common tab that we have in almost all of our modules. But the user has, again, a great level of flexibility when it comes to load combinations, and you can control the combinations separately. So for strength right here, and then for reactions right here, and for deflection combinations. So you can have these things set up a little bit differently. You can set up your own combinations that maybe your company uses, or you have your own set of different scenarios that you have to try or you want to look into. And maybe those scenarios repeat themselves on multiple projects. You can actually create a load combination set. Like those ones are the default ones, the IBC 2018 or whatever, but you can create your own, just call it XYZ load combination set, and that can be saved in ENERCALC that you can use in all of your future projects and never have to recreate it again. So that's also a possibility for those who mess with load combinations. So going to the results, because that's the fun part. Going to results right here, you have extreme values. That's the one that we want to look at because there's a lot of information you can get here, including stresses, the displacement, all of that along the length of each member incrementally. So that's too much information sometimes. But if you want to look at the extreme values that we're looking at here, looking at joint displacement, you can see joint number 1 and joint number 4. That's where the foundations are. That's the bases. You can see X and Y displacement is 0, X and Y displacement is 0, and there's no rotation. There is some displacement. For example, the frame, the drift here is 1.6 inches, and that's based on D plus 0.6 wind. If you want to change that, you can change it to maybe 0.42 wind if you want, but you can see that information right here, and you can tell that there is a little bit of rotation in the frame, which makes sense. This is a moment frame after all. And that's where you get all that information for joint 2 and 3. Moving on to the reactions, and this is the part that I was telling you earlier, is that the X reaction is right here, the Y reaction right here for the bases, and there's zero reaction, zero rotation or zero moment at the base. So to move on, there's just a lot of information to cover in here, of course. You can click on the extreme values again, member forces, stress checks, and you can see that all of your members are passing, and you can get a lot of incremental results. And for a lot of us, whether you're designing your own connections or you're delegating connections, you can click on the member and forces, and you can see here the moment that's going from the beam to the column and from the column to the beam. So this way you can design those connections properly. The last couple of things I want to go over here is the is under the sketch tab, where you can see the undeformed and deformed shapes. You can click on whichever load combination you want, and in our case, we want to pick the deflection load combination. That's this one right here. And you can see the deflected shape, and it's clear that the base is pinned. There's no questions about that. So at least we have a good visual confirmation that we are comfortable with. And this is just another thing that I did on my own, where it's a fixed base, and that's actually what it looks like, which makes sense. And of course, you get less lateral displacement at the top. And of course, another great assessment tool is the diagrams. So you get axial, moment, shear, and deflection diagrams for each member that you have in your project or in your frame, and then you pick whatever load combination you want. And you can get the stress, you can get deflection, reactions. That's for the combination, whichever you would like to use. So overall, the 2D frame module is a powerful tool that allows the users to analyze and design frames and trusses. It provides a great level of flexibility in terms of modeling, and of course, it displays a breadth of granular results for you to be confident in your design. So before I turn this to Seth, we just want to encourage everybody to dive into, encourage everybody to join our office hours. And that's a simple process by just going to our website. You can just sign up for it and make sure that you tune in for our next session. All you have to do is just put an email, and if you know your registration number right here, and you just click on remind me about office hours. And of course, you can always join and find the latest and greatest information about the next office hour session in the same website or on the same webpage. And with that, all we have here is just a reminder that we do have a recording of all of these sessions in the same webpage. Just you have to scroll down, and you'll be able to find all of the recorded, unedited sessions. So now's the time, everyone, that's been waiting for. I know this took a little bit longer than expected due to the breadth of it, but it's time for Seth to announce the Pi Day raffle winner and do questions and go from there.
All right. Thanks, Mac. So we do have a winner for our drawing for our Pi Day giveaway, and our winner is Mike Brenneman. So congratulations, Mike. We will be getting in contact with you via email to get your prize shipped out to you. If everybody feels like a big round of applause virtually for Mike. Congrats on that. Happy Pi Day in advance, everybody. And with that, we will go ahead and transition to our Q&A segment. So we do have some great questions today. First question, we did touch on a little bit about ENERCALC for Revit at the beginning of our session. So I'll go ahead and throw that one up here. How specific do you need to get with ENERCALC for Revit to work with it? Do you need to model every connection specific to each framing interaction for it to register the analysis? So I'll jump on this one, and then Mac can follow up with any thoughts he has. But the most important thing to know about ENERCALC for Revit is that it is 100% driven by the physical model geometry that you create in your Revit model to make your documents look right, to do your multidiscipline coordination with MEP and architecture. It is not fundamentally relying on model and stick analytical framing like you see in global analysis workflows. So you do have some proximity testing based on how close a beam or a column are to each other to deal with things like setting up support conditions, but you have flexibility over that, and it's not driven by a stick and node modeling workflow. Hopefully that answers your question. Mac, go ahead if you have more thoughts on that.
I absolutely agree with you. Yeah, it's really, you just have to follow, couple rules of how to model in Revit, but it's not a stick. It's not any of those outdated methods of going about business. This is completely the geometrical model and how you modeled your members, and it reads the geometry and it works out with what you physically have modeled.
All right, next question. For joint loads applied in the example, can we apply the point load in the form of a member load instead of for the lateral load? So the question is fundamentally about applying a point load on a member rather than on a joint.
Correct. So I showed you how to apply loads on a joint. You see, that's earlier, but this right here is member loads. And if you click on member loads, I don't know if you remember earlier from my example, we applied this as a dead load in the global Y direction. You can actually apply it in the global X direction, and that will make it a horizontal load. So for example, this is our member right here, and we can add a quick load, and I want to apply it global X, and let's say it's the whole thing, and I'm going to put 0.02. Oh, there you go. 0.02. I don't know if you can see that clearly. So yes, the answer to the question is that yes, you can absolutely apply that load on a member load and just apply it horizontally. It doesn't have to be a point load on a joint.
All right, perfect. Question from Lutfi. When using the module for wood truss design and analysis, will the module design truss members based on the NDS? So this is a capability we have actually both for AISC and for NDS, but go ahead, Mac, if you want to elaborate on that.
No, yeah, that's true. Um, but there's something that I don't do a lot of wood, so that wouldn't be my place. But I know there's some particular checks that might or might not take place. So if you're working on a wood truss and you're having, I'm assuming there's something that prompted the question. If there's something, please send it to the support team to check it out. But typically, it should design everything just fine. But if there's anything that you want us to look into, we can.
Also, I just want to say shout out to Lutfi Mized for past winner of one of our awesome Lego giveaways.
Yeah.
He was the
Yes.
recipient of our steel base plate finite element model.
Right.
All right. Can you revisit the unbraced length structural properties where you were setting unbraced length? Question from
Unbraced length structural properties. Are we
someone
talking?
asked. We missed about unbraced length structural properties. That probably has to do with the actual code check uh,
Okay.
analysis being
So
performed.
as you put, I don't think I talked about it, but as you put your information here for members, you get here your unbraced lengths. You can actually just put whatever you want here, and you can pick your slenderness ratios, or you can have ENERCALC auto-calculate your KX values based on the end fixities that we've already determined in our release and unreleased conditions. Um, I hope this answered the question, but yeah, as far as the unbraced length, it's just the unbraced length. So we're putting LU, LY, and we're putting all that information here, the full lengths, and then the K factors are, you can use one for all of them, or you can have them just auto-calculated. Yeah, I
Perfect.
didn't get to that while I was doing my presentation, so I wasn't sure if there's something that I said earlier that prompted this, or if
Gotcha.
there.
Okay. Do we have, or can we have a look or clearly visualize directions of global XYZ in the 2D frame? And that probably has to do with the overall sketch view.
That I'm not sure. I know and I think this is probably in the FAQ, where you can find that information. But the X and Y, like the positive is to the right for the X, and for the Y, the positive is up. Those are the global directions here. I'm just not sure if there's something here that I can display it with or not. Because I know here the Y, for example, this clearly tells you that the global Y direction acts towards, upward. Yeah, that would be a good question for support to show you where that is, but the answer is going to the right is positive X, going to the top or upward is positive Y. But if you follow up with us, we'll find you the literature somewhere.
Perfect. All right, another question here about you started out your example using the frame wizard. What different types of frames can the frame wizard actually help you create?
Yes. You have single story, single bay. I'm actually do this here. So single story, single bay moment frame. So the 3D, three stick elements. And then you have, so here. So this one right here, you get multi-bay single story, and you get multi-story frame, multi-bays. And then you get multi-story single bay. So, and then this is a continuous member. You can do that. And then for trusses, those are the current truss shapes that we have.
Perfect. And then as a follow-up to that question, can you also design or create a frame or truss not using the wizard?
Yes, absolutely, 100%. Yes. That's why it's a question that it asks you in the beginning. Do you want to use the wizard or not? The wizard doesn't automatically pop up. You would have to enable it, or it just asks you, hey, do you want to? Let me actually grab this here so you can see it. Yeah. So even here from my presentation, you get this question. As soon as you click, you get this question. If you say yes, it will take you to this menu that we just looked at. But if you say no, it'll give you just a clean module that has nothing. So you'll have to go and create all of your joints from scratch. You have 0 joints, you have 0 members, you don't have anything.
Perfect. Follow-up question on the unbraced length issue that you were going through, Mac.
And I just want to show here, you see
Oh
that
yeah, go ahead.
that's when you do it without anything, it just at zeros. There's nothing to worry to see. Okay, sorry, what was your question?
Yeah, follow-up question on the unbraced length. As Rick was pointing out, LUZ and LUY and unbraced length shows -1. What's meant by that, and what effect will it have on the analysis or the capacity checks?
That's probably a good question for support because I'm gonna have to look into it and see what's going on before I can here. I have this right here. Open. The thing is that yeah, I'm gonna have to look into this a little bit more before I give a brash answer.
Perfect. Um, there was also a question about, are there any limits or upper bounds on how many members and joints can be modeled?
Yes, there
And
is. Yeah, go ahead.
oh, go ahead.
Yeah, the answer is yes. I don't know the number top of my head,
Yeah,
but
I
we
believe
have
the
that
answer
information.
is in the neighborhood of 300 joints. It
Oh,
uses a
yeah.
2-to-1 members to joints, so the upper bound is around 300 joints and around 600 members. So that's getting to be a pretty large model. So during most typical analysis, you're not going to bump up against that limit. All right, let's see. Another question on that single bay frame you were looking at, is a 4-member frame possible? For example, adding an additional beam at the bottom of the frame. So that would be like a moment frame with a grade beam at the bottom kind of set up.
You,
So that would not be generated by the wizard, but you could still model that by
yeah,
hand and
yeah.
then place your restraints at the corners.
Member, yeah, exactly. That's exactly what you do. You see right here that says add member, and I don't want to go through this too much, but you can say here add member, and you can define the like define which joint you want it to go from, maybe from joint 1 to 4, something like that. And I'm gonna call it XY or something, and then you can start working. So you'll have to go through it because you'll have to define the materials, and there's some stuff. But yes, you can add the member. Of course, you have some issues here to fix because we just added a member. We need to fix the materials and fix the fixities as well. So, but yes, the short answer is yes, absolutely you can.
Awesome. Question from Chad: how to add more members with the wizard? So the wizard is to shorten your generation process, and then you can use that exact process that Mac just went through to add additional members if you need. So when you use the wizard, you're not stuck with that geometry. It's just a quick generation, and then you can go on and modify or extend that geometry in whatever way works well for you. And Mac, if you want to elaborate, feel
Yeah,
free.
let me give you here a good example. I don't know if you can see here my sketch. So a good example is that if I have a shape, something like this, and instead of doing all this from scratch, I can have the wizard create this, and then I can come later and just add this additional node number 5, and then add this member ABC, member D, and member E.
Yeah, and
Does
you
that
can
make
do that
sense?
with the add joint, add member workflows like
Correct,
we
yeah.
just
So you'll
went
have
through.
to add joint first, and then you'll add the members second. Because you can't, at least here, you can't model a member that's not going to a joint in ENERCALC here. So every member you do, it has to go from a joint to another. And just to give you an idea, if you want to do something like this will require a joint here, a joint here, a joint here, and a joint here. So you can't just do just 3 joints and call it good. You'd have to put a fourth one. That's why this one, you'll have to put one here and you can just build this. But yeah, it can just help you do some of your work and then you can add more to it.
Perfect. All right. Well, we are about 10 minutes after the hour, and so we probably need to go ahead and wind it there. But if there are any questions we didn't get to, I know we had a question from Jay about lifting hook embedment for precast design. That would be a great question for support. And then Cartez Engineering wanted to dig in on INJ restraints. Feel free to reach out either to office hours at enercalc.com or support at enercalc.com with your follow up questions, and we will try to get those answered for you. In the meantime, Mac, do you want to go ahead and give us a teaser and some details about what's happening next month?
Yes, let me get you back here. All right. So it looks like, yeah, next month's session is going to be April 9th. And we're excited that we've had everybody today, and we're looking forward to our next session. We're going to be covering or at least that's the plan, is to cover some miscellaneous modules. So that would be the modules that we would use for maybe the section geometry builder and the and group bolt calculator and stuff like that. So that'll be more of the miscellaneous modules because that would be a good time to do them. But yeah, we will see you guys April 9th.
All right, sounds good. As always, we appreciate everybody being here today. We always look forward to these sessions to connect with everybody. We will look forward to seeing everyone next month. And if you have any further questions or if you have requests for future topics, things you'd like to see more information about, as always, send those over to us and we'll be sure to go through those. So thank you all very much for your time, and we will see you guys next month.